Hi guys, BuildZoid here, and we're back with that GTX 980 Ti reference card that I failed to repair in the previous video. It is not repaired, but it is functional now. And all of the phases are running. It has all of the power stages that it's supposed to have. Like, if it weren't for the fact that I know how I got it, like how how I made it functional, you probably couldn't even tell that I didn't repair the card properly. So anyway, let's take a look at how I dealt with the well, we're not going to actually take a look at how I dealt with this because I didn't like film the process of dealing with this cuz I wasn't sure if it was going to work, right? So it's like Anyway, this is what the card looked like at the end of the last video. Right, so we've got this pad over here missing, which at the time I thought that was a ground pad. Turns out that's the switch node, which makes zero sense to me, and we'll go into why that is. But yeah, anyway, so that's the switch node, so that's just gone. It's still gone. The card still doesn't have that. It's fine. It runs. I don't care. And then down here, the 12-volt pad over here is a bit crunched, I guess you could say. So yeah, so this is the condition the card was in at the end of the last video. And my solution to this problem was, so this one, I just put the power stage over the missing pad anyway, because it turned, like, we'll get to that when we look at the pinout. But this bottom one was a much bigger issue because initially, like, the main problem here is that this, like, what's left of the 12-volt pad is not flush with the PCB. So you can't just like, and I didn't really do anything to like flatten it out. There are ways to, like, I guess I could have just taken some sandpaper to it and just, tried sanding it down to be level with the rest of the PCB in the area. Instead, I decided that I would just mash the power stage onto it, and that would work out somehow. And so I tried that once. It didn't work because this is slightly raised relative to the, like, this, like, it's not flush with the PCB. So the issue that I ran into is that when I smashed the power stage onto this, these pins over here, which are a bunch of, like, control signals, yeah, those didn't get connected at all. Like, the solder just didn't, like, the solder from the power stage never made contact with the solder on the PCB, and so it just never connected. Yeah, so I tried to turn the card on with that initial setup, and the phase didn't run because it wasn't getting any control signals, so that was annoying. So I pulled that power stage off. I added a bunch of solder to all of the pads and pins, and then I smashed a new power stage on, well, another replacement power stage. I'm not using actual new power stages for this. It's a 980 Ti. I'm not, like, it's a reference 980 Ti. I'm not putting money into fixing this thing. It's not worth it. It's just going to blow up again eventually. So anyway, so I just put a bunch of extra solder on all of the pads, and then I smashed another replacement power stage from that, what was it? I think it was an R9 280X that I was using for spare parts. Yeah, so I smashed a new replacement power stage on it, and now that there was more solder on all of the pins, they actually made contact when I smashed the new power stage on, and it works. So that's how I dealt with this phase. And then this upper phase, I just put the power stage over it, didn't really have to do anything, and just, if we all pretend that there isn't a missing pad, it doesn't, like, you can't really tell that. Like, actually, the only way you can tell that the pad is missing is this pin right here. The rest of it, like, you can't tell there's a problem if you don't know that I just kind of didn't bother to do anything about the fact that the pad is missing. And, speaking of the pad that's missing, that pad is not ground, which is super weird. And also somewhat less concerning than if it was ground. So here's the pinout for the power stages that are used on this card. These are, what is it? FDMF. Yeah, these are Fairchild, which part of On Semiconductor now. Anyway, these are FDMF 6823As. There's also there's a bunch of different flavors of the 6823. This is a 60 amp version. The replacements I'm using are the 6823Cs, which are like a 50 amp version, which is a slight downgrade in terms of the VRM efficiency. But again, like, it's my 980 Ti. If it blows up again, I don't care. Like, I would never do this if I was repairing the card for somebody else, but it's mine. So if it catches fire again, it's a me problem, not a me plus someone else problem, right? Because obviously if you badly repair something for someone, that's still technically your problem, right? Like, you shouldn't have done that, but anyway. So yeah, this pad layout makes zero sense to me because we have, like, this big main pad is the switch node. And the reason this makes zero sense to me is, generally speaking, with buck converters, you want to keep the switch node as small as possible. Now that doesn't really affect that doesn't involve the actual power stage itself, but like the switch node going between the power stage and the inductor should be as short as possible, because if you have a really excessively large switch node, it starts radiating VRM switching noise into the environment. And this can be a real problem for like EMI compliance, that kind of thing. So you generally do not want giant switch nodes. And consequently, switch nodes are not very good, as, like, you can't sink heat into them, because they literally, like, the goal of a good switch node is to be as short as possible and connect the power stage to the inductor as directly as possible. And that's basically all a switch node is supposed to do. The inductor is potentially a heat generating component in and of itself, so you aren't really going to be sinking much heat into the switch node, and that's why this doesn't make any sense to me. Like, why would you have such a massive switch node on the power stage? Because you can't, like, if we look at some other high-end power stages, like, say, the International Rectifier 3575, which is a 60 amp power stage, very similar to the 3555 and 3550, you'll notice, like, we have this ground tab over here. Well, that's not really a tab. We have this ground pad over here, and then another ground pad over here. Like, most of the area is dedicated to ground, because you can use the ground plane of the board that the power stage is mounted to as a heatsink. You can't really do that with the switch node, so it doesn't make a ton of sense to have this, like, massive connection for the switch node. And, like, that's what you see here, right? Like, the switch node is this tiny little edge pad. And then, like, most of the area is dedicated to ground. If we look at some other power stages, like, say, the wait, what? Why don't I have that open? Oh, there it is. If we look at something like the AOZ 5312, which is the power stage typically used on a lot of 3090s, it's the same thing, right? You have ground, more ground, tiny little switch node. And this is just basically done because it improves your thermal performance of the power stage. And then there's this thing where the biggest pad is the frickin' switch node, which I don't get it. Why would you have a giant switch node? I'm also pretty sure this is a somewhat standardized footprint, as in, like, Fairchild isn't the only manufacturer to use it. And yeah, I have no idea why this is a thing. This doesn't make any sense to me. Like, the vast majority of power stages I've dealt with will normally have a giant ground pad, because ground is good for sinking heat. Also, it connects your, like, that's where actually technically the ground pad also handles just as much almost as much current as the switch node itself does. Right? Because basically the switch node handles the current, like, for one portion of a PWM cycle, you have current flowing through V in and the switch node, and for the other portion and for the rest of the PWM cycle, you have current flowing through the ground and the switch node, right? And yeah, so, like, most power stages just have, like, a massive ground pad, and then there's this thing. So anyway, I'm not too concerned about the switch node being destroyed, because even if you look at the PCB, like, you can see exactly what I said. Like, there's not even any vias here. This is just a strip of copper that goes from the power stage to the inductor, right? Because that's what a switch node is supposed to be. It's just as direct a connection to the inductor as possible. And that's kind of that. And this via, I think, is for a snubber circuit that isn't populated on the back of the card. And I say I think because obviously I don't have schematics for this thing. So and I could try tracing it out, but I can't be bothered. Anyway. So yeah, like, so basically, you know, if we look at this pinout, we also, like, we don't need the entire switch node as far as I'm concerned, right? We have all of these switch node pins over here and here, and those are still there, right? Those are still on the card. So I just kind of smashed I just kind of put the power stage over that and called it a day. Potentially there is now more resistance in the like switch node to the power stage connection than there was before. I don't know if that's really significant. And the easiest workaround, like that's kind of the main concern with like damaged like power pads like this, is if there's not enough, if you don't have a good enough connection, right? You are effectively increasing the resistance of the power stage, which means it's going to get it's going to produce more heat than it already does. Because now you're because you obviously have the power losses in the power stage itself, in the MOSFETs of the power stage itself, as well as all of the internal like wiring. But then you also have the power losses in the actual solder connections to the MOSFET. And now, most of the time, you can just ignore that because it's a very, wide, short connection, so it doesn't really produce any heat. This right here might not fall into the category of you can just ignore that. But there's a workaround for this. If you just don't put the card under sustained load and run it with like 100% fan speed all the time, it's probably going to be fine, right? Because basically these power stages, this probably slightly reduces the efficiency of the power stage. And I don't think this actually affects the thermal performance because, like I said, the switch node really isn't meant to be sinking heat. I don't know where that heat would go. Because, I don't know where that heat would go. It's not like this card has some elaborate, clever VRM cooling system that actually sinks heat out of the inductors, which is done on a lot of, motherboard... Yeah, actually, a lot of GPUs and motherboards will actually do that. They'll sink heat directly out of the inductors into a heatsink, because while the inductor is not the world's most thermally conductive object... it does still conduct some amount of heat. It's probably more thermally conductive than your average thermal pad. And so sucking heat, actually, it might not be. Because the thing is, inductor cores are built, are sintered metal. So... yeah, it might actually not... I don't know what the thermal conductivity of the average inductor is. It's probably... It's not... Definitely not on par with, solid pieces of metal. But I wonder if it's probably better than some thermal pads. So, sinking heat out of the inductor into a heatsink is a totally sensible design decision. But this is a EVGA 980 Ti PCB. This card ships with a heatsink with this heatsink. And the reason the VRM blows up so much on these cards is because this is the VRM cooling. It's literally a metal plate. It adds zero surface. Actually, no. No. In terms of surface area, this has the same amount of surface area as the PCB itself, because it's the same damn size and the same damn shape, right? In fact, I think the PCB might have more surface area because you have all of the irregularities of the various components sticking up off of the PCB. However, this being an aluminum plate, it should have a better thermal conductivity than the PCB, so it's debatable as to this being even effective as a heatsink. Either way, it doesn't dissipate any heat from the inductors because it doesn't make any contact with the inductors, and neither does the heatsink, the main heatsink itself. The backplate doesn't try to cool the VRM either, and at this point you can totally see why it is that these cards tend to have their power stages fail. To be fair, even the reference blower cards will sometimes have the power stages fail, but these 980 Ti SC cards from EVGA are notorious for this. If you find one of these that's dead, if you find one of these listed as dead on eBay, you are pretty much guaranteed to have a VRM failure because, this is the VRM cooling. I don't know what else you would expect. Anyway, where was I going with this? Yeah, so I don't actually think the thermal performance, that the thermal properties of the VRM on this card have gotten significantly worse thanks to the pad missing. But yeah, this is definitely not ideal, and so I've basically put a sticker on the card with a warning that it shouldn't be put under extensive load, which is a warning for me because I'm never I'll probably run the card into the ground before I consider getting rid of it. Actually, no, I wouldn't get rid of it just because it's in this condition, just straight up. No, Like, I don't want somebody else to have to deal with this thing. But yeah, so this thing's never, like, the label is for me. Basically, run the card at 100% fan speed. Do not run extensive load testing, because it might blow up again. Actually, it would probably blow up again. Like, this blew up before. It had this messed up, like, power connections that it has now. Anyway, here's a photo of one of the power stages installed. I unfortunately didn't have the foresight to take a picture of the car, like, of the state of the VRM before I fully reassembled it. And you've probably noticed that the inductor over here is nudged forward a little bit. And that's literally because I was having a hell of a time getting in between this component over here and the inductor pad when soldering it. Actually, I think it might have been just so that I could get better... Basically, I wanted to get better contact with the pad for the inductor. Because using hot air to solder inductors is... Like, it can be done, but it sucks. It really, really sucks. It's... Because inductors have a huge amount of thermal mass, and so heating them up takes forever, and there's, like, polymer capacitors right next to this thing. I don't... Like, these are probably kind of damaged already, because these capacitors would have seen most of the voltage spike when the power stages failed, so there's a decent chance these are kind of broken at this point. But yeah, like, I don't want to cook them for the sake of the inductor. So I've shoved the inductor forward using the soldering so that I could just solder it into place with the soldering iron. Anyway, so yeah, that's how I dealt with the PCB damage that I caused. Like, on one hand, the power stages did weld themselves to the PCB. On the other hand, there are ways to deal with welded power stages that don't involve ripping off the pads. I just couldn't be bothered, because I got the card for 25 quid. So it's not really... If it dies completely, it's not a huge loss. I wouldn't have considered... Like, it's a reference 980 Ti. There is no world in which I would consider this much of a loss. It's a reference, like, unless I paid, like, a lot of money for it, which is why I didn't want to buy a working one, right? Like, there are working reference 980 Ti's on eBay. I wouldn't pay money for one because they do this all the time. Like, this is really not rare enough for me to be willing to buy, like, a full price reference 980 Ti. Anyway, let's go back to the camera. Man, this video is going to be very, very long. Now I want to show you that the power stages are, like, actually running. Because the thing is, anyone can just smash a power stage onto a PCB and go like, oh, it's fixed now. If you just don't check that the power stage is actually running. Because like I mentioned earlier, when I first tried to install the power stage with the damaged 12-volt pad, it didn't run because it wasn't making contact with the control signals, which is why I had to add a bunch of solder there so that it would actually make a connection. But yeah, no, it does run. I've verified with the oscilloscope, and I will show you right now. And I have forgotten how I wanted to set the... Ah, right, that's what I wanted to do. Like this. There. So you can see the oscilloscope. And I'm going to be poking... so basically... Oh, man, this is... I should have taken a photo of the card for this. Too late. I don't feel like starting the video over. Oh, it's on autofocus. There we go. Also, the card is currently running. Right. So. We're actually going to put the oscilloscope on top for now. And I'm just going to poke the card. Man, I don't have the... This is going to be so awkward. I really didn't think this through. Yeah, the mic can barely reach this far. Okay, here goes. Don't... Oh, man, the HDMI cable's in the way. Okay, wait, how am I gonna... This is awful. This is why I hate making videos. Oh, no. Like, the logistics of filming... I mean, I guess if I decided to start editing my videos, I wouldn't have to fight with deal with the logistics of not editing anything ever, but yeah, anyway, so basically there's so you can't, okay, so the circuit we're probing is a similar, well, so the thing is, NVIDIA didn't populate this, or EVGA didn't well, no, the thing is, I've never seen it populated on any 980 Ti or Titan X Maxwell card, so it's straight up like NVIDIA, EVGA, nobody who's ever used this PCB populates this part of it. Basically, we have these empty pads over here, right? Like, you see those, the R... Can I zoom in more? The answer to that question is no. Right, so there's these two big pads, right? Like right in front of my finger, those two big pads. Those are for a large resistor, similar to what we see over here with this little capacitor over here. And this capacitor resistor circuit is called off the top of my head, is called a snubber circuit. The point of this is basically when you have a buck converter, if you have a really fast switching MOSFET, if you have really fast switching MOSFETs, the inductance of the power, like the switch node and the MOSFET packaging and the inductor can basically lead to a really nasty voltage spike on the initial turn on. So, you know, the MOSFET is only switching 12 volts, but you can potentially end up with the switch node seeing voltages as high as like 30 volts, which can break certain MOSFETs, especially when we're talking about VRMs designed for low output voltages, right? Like the MOSFETs in this VRM are probably only rated for something between like 20 and 30 volts. So if there's a like ringing, like a voltage spike due to ringing due to parasitic inductance that's like 30 plus volts, which can happen, it would damage the MOSFETs. And so the workaround for this is a circuit like we have here with the little capacitor and the resistor. Basically, that filters out some of the ringing noise and limits how high the voltage spikes can get when the high side MOSFETs switch on. Now, on this card, it's only populated for the memory phases. Like the memory VRM is right here. So those two, like, and the memory VRM uses like different, is made up of discrete MOSFETs, uses different inductors, different power planes. So that has a snubber circuit. Whereas the actual main vCore VRM, it doesn't have that circuitry because evidently it's not necessary. The electrical properties of the power stages and the inductor just translate into not having ridiculous, you know, like turn on ringing spikes, and so they don't need the snubber circuitry. Or maybe they do, but they decided to not use it. Well, I don't know. I've not investigated it. Evidently, something like they decided that they don't have an issue with excessive ringing on the phases, and so that circuitry is populated. But we do have a direct connection to the switch node from the back of the card here, so we can actually check if the phases are running by probing the capacitor end of the snubber circuitry, which isn't populated, but yeah. So anyway, I'm going to go poke that, and we should see the switching waveform for one of the phases. This is one of the, down here we have phases that I didn't actually repair, right? I repaired the top edge of the PCB. Well, my repairs were around the top edge of the PCB. So right now we're probing one of the phases that the card just comes with from the factory that I didn't have to deal with. There, and it's worth noting that right now, the way I have the oscilloscope connected to ground is suboptimal, so that might be exaggerating the upward voltage spike that we're seeing on the oscilloscope right now. And actually, I'm just going to stop it. Oh. The thing is, if I accidentally slip off of the pad I'm trying to probe, we're going to have a really bad day. Or more like we could have a really bad day, which is why I hate doing this kind of thing on camera. And it's not like I can add an extension wire or something. Yeah, so here you can see why they haven't bothered to put like a snubber circuit, because that's peaking at 18 volts, which is perfectly, like, that's fine. You don't need a snubber circuit, right? Now, if this was peaking up here, that would have been a, if it was hitting like voltage spikes up into this area, that would have been a pretty bad design decision to not populate this circuitry on the back of the card. But basically, like when they were designing the PCB, and I've actually read some like guidelines on how this stuff is supposed to be set up, because I have occasionally had cards where some of this, like, they'd have damaged snubbing circuitry like this, and it's like, can I run the card without that? It's like, no, you really shouldn't. So basically, the PCB, when they're designing it, the thing is, as far as I know, it's actually relatively hard to like calculate how the VRM will behave when it comes to these like turn-on spikes ahead of time. So basically the like technical notes or design guidelines, whatever I read, basically said like you build your VRM and then you measure it with the oscilloscope, and then there's some equations that you can calculate like optimal, like a range of viable capacitor and resistor combinations that should get the spike under control. And then you can experiment with basically populating those onto the card. And so that's why that that circuitry is present on the card, but not like the components for it aren't populated, because at some point during development they were like, yeah, we might need this, and then it's like, oh, we don't actually need this, and so when you actually get these cards, it's not there. And it's fine, because as we can see from this oscilloscope shot, like, it's admittedly my probing technique right now is very far from perfect. So, but even then, like, we're not really seeing anything that would be like, oh, you really need a snubber circuit on this. So, anyway, let's now move on to the phases that I did actually try to like the phases that I attempted to repair, yeah, I'm going to run the oscilloscope, and we're going to run the GPU-Z render test. I do have the fan speed on the card maxed out, and the reason I want to run the GPU-Z render test is because like, NVIDIA cards have weird like, phase shedding. AMD GPUs have, like, very predictable... Well, actually, no, AMD GPUs are also... It depends. There is no such thing as like, oh yeah, you can always expect something to behave this way, because like I've seen GPUs where the manufacturer just couldn't be bothered to implement an automatic phase shedding function, so all of the phases are running all of the time. And then I've also seen GPUs where like the card, or I've seen cards where they either run like they have like a low power state mode and then a high power state mode, nothing in between. And then there's also cards which will like ramp up like one phase at a time. Which is kind of ridiculous, but that is a thing that, some GPUs will do. And so, unfortunately, it is, like, off the top of my head, like, so you sometimes need to put the card under load, and I think this card does have some amount of power management on the VRM, because I've been having a hard time reliably getting the phases measured. So we're going to run the GPU-Z render test, which doesn't pull... Wait, that apparently pulls 160 watts. Hopefully, like, the fan speed is maxed out, so hopefully the VRM won't catch fire on me. Well, actually, no, it shouldn't. I've run Firestrike on it. It's fine. Ish. I mean, it's not fine enough that I'd want to ever give this card to anybody else, but I'm willing to tolerate the current condition of it. Also, I wanted to get this a bit larger. I also pull the trigger in so we can actually see what's going on. So that's the top phase. So that's the phase with the... Got some power management going on, but that's the phase with the missing switch node. And here we have the phase with the broken 12 volts, right? And man, that VRM is already hot enough to like be painful to rest your finger on it. So, it's not that painful though. probably approaching like 50 degrees Celsius at this point. Admittedly, the card like there are modern GPUs running the GPU-Z render test pull a lot less power than this does. So anyway, yeah. So all of the phases do actually run now. They've been repaired very questionably. We can put the oscilloscope away. We can put away this. The video is going to be an hour. Congratulations, me. Anyway, I want to actually... Like, I don't want to run the card with it resting like this on the desk. It is lifted up so that the fans can actually get some air, but I don't really like running it like this. So we're going to turn this off. Also, I want to give you a quick look around the card. There we go. So I'm just going to undo... So in order to get a ground connection for the oscilloscope, I basically stacked some M2.5 millimeter, like M2.5 standoffs. And that's what I connect, like, the crocodile clip went to this, and that went through that screw hole. Anyway, we're going to put the screw that belongs there back. I'm going to get rid of the riser. Okay, so I've added some probe hookups for the oscilloscope because the main reason I've wanted a reference 980 Ti... So the main reason I've wanted a reference 980 Ti, and actually, let me just bring this up. So yeah, you can see on that capacitor, I have little hookups for the coaxial for the oscilloscope, because the main reason I wanted a reference 980 Ti PCB for testing is because quite a while ago, I basically got sent a dead GTX Titan X Maxwell by a fan of the channel, and I e-powered that Titan X Maxwell. And that card, there's a video showing that card in action. And the thing with that card is it clocks like garbage. And one of my theories as to why it clocks like garbage is because the voltage regulation is terrible. Because it is. And why would the voltage regulation be terrible if you've installed an e-power? Well, in my case, like, I did end up actually desoldering all of the capacitors. Like, yeah, I think I desoldered all of the capacitors that the card originally had. So that didn't help. And the reason I desoldered those was so that I could get better, like, ground and power connections. Another concern is, like, maybe there's too much inductance in the way I connected the power board to the GPU. Maybe the PCB of the GPU itself is actually a power delivery bottleneck, and that's made worse with the e-power. And I also took some oscilloscope measurements of that card, and the voltage regulation on it looked absolutely horrendous. And so ever since then, I've been kind of wondering, like, so what is the expected level of, like, voltage regulation for a 980 Ti or a Titan X Maxwell? Like, how bad is it supposed to be? Also, the reason I e-powered that dead Titan X Maxwell is because, just like this card, it had an exploded power stage. Also, that card is where this heatsink came from. Yeah. EVGA sold, like, an upgrade kit for Titan X Maxwell cards that was this heatsink with the VRM thermal buffer plate. You can't really call it a heatsink. It adds mass. But it doesn't really provide any extra cooling, so thermal buffer plate, not heatsink. And yeah, so this had an exploded power stage, which was on the bottom edge. This is actually, yeah, you can see the EVGA logo right on the PCB right there. So, yeah, these are bad. This is a terrible heatsink design, and this VRM isn't great to begin with. So, you know, those two factors put together lead to dead power stages. Anyway, yeah, so I've just been wondering, like, like, what is the expected level of voltage regulation for, like, a normal 980 Ti? Because I have, like, a Lightning 980 Ti that I got on eBay and then broken 980 Ti Lightning that I repaired. That thing works great. Like I got really lucky with that one. It just had like a crack in, like somebody just broke off a corner of the PCB and it disconnected, I think, the 5-volt rail from, yeah, it just disconnected part of the 5-volt power delivery. And so the card wouldn't turn on at all, but that was a super easy fix. I also have a Matrix and I also have a Kingpin Edition 980 Ti. But the thing about all of these 980 Ti's is like these are custom cards with much, much better power delivery than what the reference 980 Ti has. And so you trying to, like, I don't want to use those as like a like target in terms of like power delivery performance because it might not be achievable, right? Like I want to know like how good can the power delivery possibly get on a reference 980 Ti PCB? Because if the e-power on the Titan X Maxwell is like way behind the reference design, yeah, I've got to do something about that. If it's way behind a Matrix or a Kingpin edition or a Lightning, that's just kind of a given. Like I would never expect it to be able to compete with those cards. So, yeah, that's why I've wanted a reference 980 Ti for ages. Now, unfortunately, there's a decent chance that the capacitors on this thing are shot, but you know, we can, and the reason I say there's a decent chance they're shot is because I've already measured this thing, and it's bad. It's really, really bad. I think this might be the worst GPU I've ever measured with the oscilloscope, except for the original configuration of that Titan X Maxwell, which I think when I first turned that card on, I think that was hitting like 500 millivolts peak to peak. Unfortunately, I'm an idiot, and I didn't write down any notes about the performance conditions of that Titan X Maxwell card, so yeah, I'm gonna have to like remeasure that thing someday, so that I can compare against this. But this is really bad. Like, as far as like GPUs that like, and I have some really like old eBay cards, and they nothing. I've never measured a card with voltage regulation this bad. That's like not e-powered because that's like power like that's running on its own power delivery. So anyway, let's hook up the oscilloscope, which this is just a piece of coax with a 50 ohm termination at the oscilloscope because I do use a rather cheap oscilloscope, so it doesn't have like it doesn't have a built-in 50 ohm termination option anyway, so we're just going to plug that in. Throw the card onto the board. And, right, we need the HDMI cable. There we go. And I'm going to bring the oscilloscope shot back in. Actually, we're probably going to, yeah, we're just going to look at the oscilloscope at this point. So, you know, at idle, it doesn't look too bad, 20 millivolts peak to peak. That's what you'd expect. That's kind of that's basically as low as it gets in my experience, or 10 millivolts. Yeah, like that's what you'd expect. However, running load on this thing is, I mean, it's got afterburner open. We need to max out the fan speed. I really don't want the VRM catching fire again. You might have noticed that like the thermal pad that I have on the... Actually, can you see it from this angle? Yeah, you can kind of see it. So the pink thermal pad that I have on the VRM is like extending way past the VRM, like way past the power stages, because also it's a bit thicker than what the car... Is it thicker? I think it is. Basically, because of just how bad this VRM is, I want to try sink as much heat from the PCB as possible, and so having the thermal pad just like cover up as much of the ground and 12 volt power plane that's on the top layers of the PCB in that area, or on the top layer of the PCB in that area is sort of my like attempt at improving the heat dissipation. I've also added some thermal pads on top of the plate to the VR, like to the main heatsink. I don't think those actually do anything. I'm not sure that those actually achieve anything, because the heatsink is a bunch of fins, and so those thermal pads aren't really making great contact with it. Anyway, that might be something I'll mess around with testing on this card, but the main reason I got this card is the power delivery. And yeah, and like I mentioned earlier, there's a decent chance that the capacitors on this thing are toast. Oh, actually, okay, I'm not running it at 100% fan speed. That is infuriating. It's very loud. Also, I think one of the bearings is dying. It probably didn't, yeah. Oh, well. Anyway, so we're just going to run some 3D Mark on this. Fire Strike, because this is that Windows install that is very broken. NVIDIA control panel works. I guess we're running superposition then. This is a very bad idea. I don't know, like 980 Ti's are kind. I don't know what to expect. Let's try 1080p high. So generally speaking, good voltage regulation on a GPU is under is like 200 millivolts peak to peak. This is more like 400 or approaching 400, and actually superposition's really not that bad. Man, why is that fan making so much noise? Yeah, so this is not great. Is that actually now I really want to run Firestrike because this is looking way better than what I saw in Firestrike. Maybe 3D Mark fixed itself. It did. Cool. Yeah, we're gonna run Firestrike because I remember seeing like over 400 on this thing. And there's a chance that depending on like how the workload interacts with the that is one of the that's a thing, just like depending on how the workload interacts with the transistors in the GPU core, you get different power transients. Yeah, that's more like it. 450. Right there. 452 millivolts peak to peak. I mean, I'll reset the monitoring, but yeah, it's over 400 millivolts. Like, now that might be some kind of power management thing going on. So let's max that power limit. And actually, at this point, I'm just gonna have to live with the fan noise. I really, really don't want the VRM catching fire again. I've spent way too much time recording this video and we're trying to get like fixing this card. It's not worth it. Yeah, no, it's just bad. It's just really, really bad. Also at 100% fan speed, for some reason, the fan speed occasionally dips. Which is super weird. I don't know why it does that. I think if we max out the core voltage slider and the fan speed again. Because if the average voltage goes up, our power consumption should go up, and so the transients will get even worse. Oh yeah, they did. Also, the voltage hasn't changed. It was like 1.17 before, and now we're at 1.18. You gotta love the NVIDIA placebo sliders. Right? Like, they're just there to make you feel good about yourself. Yeah, so yeah, this thing's awful. Like, the voltage regulation on this thing is absolutely atrocious. Now, admittedly, the capacitors might be shot. But, man, let's reset it. I'm just gonna run the fan speed pretty high again. The weird ticking noise from the fans is gone. That's nice. Yeah, because I want to check the average voltage. So with the maxed out voltage slider, it was 1.18. I didn't really think to pay too much attention to it at the time, so But I think it was 1.17 without adjusting the voltage slider. Right? Oh no, it was 1.14. I mean, that's still not 87 millivolts. It is less voltage, but it's not 87 millivolts. Yeah, okay. It's like 50 milli. That's not even 50, it's like 40 millivolts. So, okay, it's not the voltage slider isn't a complete placebo, but yeah, anyway, so the voltage regulation on this thing is terrible. And like I mentioned, the capacitors might be shot. And so what I want to do next is basically mess around with like adding more, like technically the correct way would be to replace the capacitors that are currently on the card with new capacitors, but I don't want to spend money on this thing. So instead what I'm going to be doing is I'm just going to add a bunch of extra capacitors to see like how much it is possible to improve the voltage regulation of this PCB as is. Right? So if I can get this down to, and also actually I should take some measurements from the Matrix, the Lightning, and the Kingpin edition so that we have like a, like how much better could it be comparison point instead of just like, well, this is really bad. Can it be any better type thing? Yeah, anyway, so the card now runs. I will be doing I want to shoot a video of actually installing the extra capacitors on there. Maybe actually we'll go back and forth between like installing capacitors, taking a measurement. That'll probably be like a multi-hour. That could end up being a multi-hour video depending on like how bored I am, pretty much. If I'm really bored, I'll be if I'm extra bored, I'm perfectly happy to mess with like capacitor configurations for hours. Yeah, I'd say definitely hours. You know, just sort of going back and forth, like put some capacitors on, put it on the test bench, take a measurement, take it off the test bench, put more capacitors on, put it back on the test bench, that kind of thing. So I might do a video of it, maybe the entire process, probably just part of the process. I already have a rough idea of what I want to throw at the card. I'm probably just, like the easiest, like this is so bad that I think if you just throw a lot of capacitance onto this, it'll make a huge difference. Like I don't think I need to go with anything super fancy. Because it's awful. Like it's 400 millivolts peak to peak. 400. Like, I can't believe it runs. Mind you, it does overclock. With this level of voltage regulation, it can actually overclock. It'll do like 1400. I think it tops out at 1400 for the core. Should we do it? You know what? Let's screw it. This video's like, screw it. We're gonna overclock it. Just for Firestrike GT1 and 2. So we're going to start, like, first we need to figure out what this card runs stock. It's the one annoying thing with the boost system is you don't, like, since the clocks are in offsets, you don't actually know what you're going up to. So we're just going to run the render test. And we're running 1300. Man, the fan speed ramps up and down based on what the card is doing. That is super weird. Like, it slowed down when I started the render test for a little bit. I have no idea why it did that. Anyway, we're going to max everything. The 100% fan speed is unbearable. So right now it's running 1342, so we're going to do plus 110. It'll be 1451. I don't think it'll run that, so we'll try 93. 1434. I think it, like, I think it should run 1434. It should. So, yeah. We just want GT... Like, GT2 is primarily a core, memory stability benchmark, so we shouldn't need to run that. Kind of want the oscilloscope back in frame. Oh, it just crashed instantly. Yep. Yo. Okay, yeah, so 1430 too much. Yeah, this card's really bad. Like, it's even worse than the E-powered Titan X Maxwell. So maybe it is possible for these to just be super duper bad. I don't know. I think the system reset itself. Nope. Oh, I can't see if it's restarting. I think it's restarting. Yeah, the driver reset shortcut doesn't work. Yeah, so the card locked up, so that's fun. So yeah, like like I did a little bit of pre-testing. So yeah, 14. I remember. I think 1430 was the limit, but I guess I might have. The thing is, if I tested 1430 without the extra voltage, it might have actually been behaving differently. Yeah, that's kind of the thing. It's just like, okay, go. I need to buy earplugs so that I can deal with cards like this thing. Or the various blower GPUs. Gonna do plus 75 this time. That should work. Or not. What the hell? Well, that's new. Did the drivers recover? Hey, it recovered! For once. I get the feeling the extra core voltage is causing issues. Because it wasn't this bad when I first tested it, and I don't think I was messing with the voltage slider. Or I didn't touch the power limit slider. One of the two. Though I think it might be the voltage slider in this case. Unfortunately, we can't do this like the lazy way where you run Firestrike windowed and then just tweak the clock up in Afterburner while it's running, because that I would consider that extended load. Man, it's really bad. Maybe I didn't reapply the thermal paste properly? I'm not entirely sure why it's crashing so much right now. Like, it definitely could overclock. I must have done it with the stock power limit. That must be what I did. Because that would explain so much. Like, if I tested it with the stock power limit, then that would explain why why it's not working right now. The thing is, I was definitely able to overclock it at one point. So I don't know why it's like being so much worse right now. We're just going to run it windowed. I want to see what's going on. Max. There's a chance it'll crash before we see what went wrong. It's like the main concern I have right now. It's only hitting 30. Why is it? I wonder if it's upset about the capture card. Because I've had that happen with NVIDIA GPUs where they'll, like, complain about what they're connected to. Well, okay, you know what? Maybe we should just do a run at stock, just to verify that the card still works. Like, this is kind of behaving like... Like, I'm wondering if it's, like, bad thermal... Like, bad heatsink contact. Because that's kind of what it looks like to me right now. I'm just going to raise the fan speed, and we will not do anything else. Like, it runs at... Like, it should run at stock. Right? Yeah, still 400s on the peak to peak. I'm gonna have to check the thermal paste application, I think. Because I'm pretty sure it did 1400. It might not have done more than that, but... Actually, I might be misremembering things. I definitely checked the card with the oscilloscope before making this video. But did I overclock it when I did that? I don't know. I don't think I... That doesn't, no, that doesn't sound right. Because it's like, I don't think there's any GPU that I've ever, turned, if I've gotten as far as installing the drivers for it and running Firestrike, I think it's almost impossible that I didn't try to overclock it. Because that's just how I am. There's no way. So, right now it's probably misbehaving because of... I guess moving the card, like, maybe messing around with the card a bunch... For shooting, I might have, like, screwed up the thermal paste application or something. Yeah, like, it runs stock. And it scores correctly. If I'm not mistaken, these should do, like, 2,000 on the memory. Actually, aren't these the wacky cards where, like, the memory clock affects core clock? I don't run a lot of NVIDIA, by the way. Just, like... Or I'm more like, I don't have a lot of NVIDIA history. Let's just put it that way. Now it runs. No, it doesn't. Yeah, I think the thermal paste application must have gotten screwed up while I was messing around with the card. So anyway, that's it for the video. We're not going to try to fix that right now because the video is long enough as is. Or actually, it's way too long. But yeah, there was a lot of information that I wanted to stuff into this. Just like releasing this as a yeah, there was just a lot of stuff I wanted to cover. So that's my excuse for why the video's an hour. I don't know why I'm even making that excuse because with all probability, most people didn't make it to this part. So I'm not sure who I'm apologizing to. But anyway, if for some reason you liked this video, and you'd like to support the channel, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store, where I've recently added some new hoodies. And then there's also t-shirts and posters, you know, the usual YouTuber merch. And I also have a Bandcamp, where you can listen to things that sound a lot like Coil Wine or fans at 100% fan speed. Anyway, that's it for the video. So thank you for watching. Like, share, subscribe, and goodbye.